Good morning, ladies and gentlemen, and welcome to this live session on Digital Earth Africa platform. The topic of today is on water quality monitoring located in Lake Ahme. Water quality monitoring is an essential step in protecting human health and ecosystem and ensuring the sustainable use of this precious resource. Like it is said, water is life. It involves regularly collecting information on the chemical, physical, and biological parameters of water, and also allowing the assessment of its condition and detection of potential pollution. The United Nations SDG Indicator 632 titled Proportion of Water Body with Good Ambition. For management decision, there are many methods for measuring water quality using remote sensing algorithm. In this our context, we will use the algorithm generally estimated to estimate the amount of suspended matters in the water. That will help to determine whether efforts to improve water quality are paying off. Lake Ahme will be used in our case study. Lake Ahme is located in Bopa, and domestic pollution is very significant. On this site, 750,000 fecal coliform were counted per liter of water. And this data indicates that the water of Lake Ahme is the most bacteriologically contaminated in all of southern Benin. The data and methods we will use for this work the Landsat 8 OLI operational land air measure and the TIRS thermal infrared sensor and the water observation from space WOFS. Water observation from space is a service that uses satellite imagery to provide historical observation of surface water across the African continent. And it is good to monitor the water through time to be able to assess the quality. What is the benefit of the Earth observation system, which Digital Earth makes available to all users? Through these methods, 3 empirical algorithms and a spectral index regarding total suspended matters in water are used in this work. These algorithms were developed for a specific region of the world and are not necessarily universally valid. That is also the purpose of this live session, so that the different users located in different parts of Africa will try them and test how this method is working, so that we can have a better approach and see which method or algorithm is more suitable for monitoring water quality. We are expecting your contribution and sharing your experience of using this notebook. Landsat 8 data is a surface reflectance product. Because water has a very low radiance, the accuracy of the result can be affected by slight variation in atmospheric condition, differences in atmospheric correction algorithms. The color bar in this result have been removed to avoid displaying specific quantity for total suspended matter. The water quality algorithm we are going to present or we are using in this notebook are the limb burner total suspended solid, TSM, the suspended particle model, SPM, the normalized difference suspended sediment index, NDCI, and quant total suspended solid, the TSS. In our context, to execute our analysis, we have organized our notebook into cell and write with programming language, which here is the Python language. First of all, we will import the Python package used for analysis. As usually, we have to load the package through matplotlib inline we import the data cube for access to the imagery. We import the NumPy as NP, import XArray as XR, we import the GeoPandas as GPD, and also we import the matplotlib.pyplot as PRT from the odc.geo import geometry, but also from Digital Earth Africa tools.plotting import display map RGB for the presentation of the result and other elements. The database, DataCube database, will allow us to load and display the stored Earth observation data. So we will, in this script, you have to run the DC equal datacube.datacube app monitoring water quality. For the setting of the analysis, you have to define your area of study. And for that, you have to indicate the latitude. Here we use the central latitude to analyze, the central longitude of the area to analyze. We define the lat buffer, long buffer, and the time range, that is the period we want to analyze. Using the format of year, YYY, MMDD, that is the year, the month, and the day. There are some observations that has been made. You can use the first original notebook before it has been formatted for this purpose. And for that, you have to consider the water quality of the Lake Ahme. For this one, to run it, we are using the Landsat 8 data, and you have to be indicating that data. You have also here some suggestions on area you can run and see how the water quality will be. There are some areas that have been defined, like the Lake Nokwe in Benin, Weja Reservoir in Ghana, and for this purpose, we are focusing here on Lake Ahme in Benin. The coordinate have been defined, and the buffer also have been defined. For the selection of the area, like we mentioned, we have indicated the latitude and the longitude, and we have also defined the buffer. But we have also two options in defining your area of interest, either by specifying the latitude, longitude, and the buffer, or by using your shapefile to delineate your specific area of study. So you may use a GeoJSON data or the S3 shapefile data. But for that purpose, you have to upload using your S3 shapefile all the associated file as .cpg, .dbf, .shp, and .shx. If you miss one of these elements, the loading or the delineation of your study area will not work accordingly. Now we start running it. Here on this aspect, the first method here, we have indicated the longitude, latitude, and the buffer zone. We have created a geopolygon and a geodata frame for the area of study by defining the CRRS with here EPSG 4326. And on the last one, we have defined the lat range and the lat long range. The period of time here, the time range here, we just indicated the year, that is 2020. We have here the location indicated, and the frame in red indicates the area we have chosen to work. We are now going to load the data. Load ARD function enable us to gather the satellite imagery, and we will have our XArray.dataset that will contain only the observation with a minimum percentage of good quality pixel. You have to know also that when you are using your satellite imagery, you try as much as possible to have less cloud cover on the image, and it is indicated at least to have not more than 10%. That is, your image should be 90% free of cloud to enable a good processing and analysis of your result. For that now, And once we have defined those parameters and we have identified that our area study is well located, we will define a query dictionary by indicating the longitude, latitude, and the period as indicated above. In that query, we define the X long range, the Y lat range, the time that corresponds to the time range, the resolution minus trend. Here, you have the minus trend due to the fact that you are using Landsat 8 imagery, and we align it to 1515. We identify this the projection system, and we define the output CRS, most common CRS, DC equal DC, product Landsat 8 SRS, surface reflectance, based on the query equal query. We will load the data available by using the DS load ARD, DC equal DC. The product is Landsat 8 underscore surface reflectance, SR. The measurement we will use here, the wave, the band red, green, blue, and near infrared, and we group them by solar day. The dask chunk, we put it as time equal 1, X equal 2000, and Y equal 2000. The output CRS equal the output CRS we have defined earlier. And the minimum good data equal 0.9. That coincides with the 90% we have indicated earlier. And we close our query. After we have executed the cell above, we will obtain a message that will indicate the pixel parameters of the pixel, the counting of good pixel we have, and the filtering of 1 out of 18 time step with at least 90% of good quality. Applying the pixel quality cloud mask, we will rescale the Landsat C2 data and we return 1 time step as a dask array. We will use the pixel quality setting for USGS collection 2, and we search for dataset Landsat 8 SR after counting the good quality pixel, and we have our result. This is completed, and we print the DS, and we have this information. Dimension give us the time where we have 1 image for the 2020 period, and the data variable where you have the red, green, blue, and near infrared. And for the attribute, you have the coordinate reference system. Here, the EPSG 32631 that gives us the location and the zone in UTM. We will load also the water observation from space. To ensure that water quality measurement algorithm only apply to water area, it is useful to extract the water extent from the WRFs product. The water extent can be used through the geomedian composition so that water quality indices are only displayed for pixels that contain water. So we have a code here where water is equal to 128. So we will load this data from WRFs by water equal dc.load product WRF ls group by solar day like ds.geobox, and we define the data dask chunk. The collection category is equal to T1 and the time equal to query time dot water. We extract the mask for the area classified as water extent equal water 128, and it should be squeezed. And we print the result. We have the result here, xarray.data array water time we have 36, and we have the size of the frame that have been defined, and all the other related parameters concerning the coordinate, the time, the X and the Y, and the spatial reference. Now we consider the DS1 and the DS2 as a dimension in time. So we have the date 1, ds time dot value, and date 2, water extent dot time dot value. We will find the date that are common by intersecting. So we write the common date equal np dot intersect id 1d date 1 and date 2. A filter will be made on each of those data sets to keep only the common date. So for water extent equal water extent dot select true time equal common date. and we have the water extent. And on this part, we have the result water, and we have one result time equal 1 and the frame dimension. Now we are going to display the geomedian composition and the water extent. So we will define it as fig AX equal plot dot subplot 1 to fixed size. We define the size of the figure 12 and 6. We will display the image in a true color by defining it through RGB equal DS, comma, AX equal AX0. We will represent the extent of water through the WRFs by defining it through water extent dot plot AX equal AX1 C map. Water will be represented in color blue, and we want the color bar as false. We will now give title to all those frame and the result we will have. AX0, we will set the title as geomedian mosaic and all the parameters to define it. And also AX1, we set the title water extent. So these are our results for the geomedian mosaic. On the left side, where you have the image in color composite, RGB, and the extent of water is where you have those patches of green and light green up to the north that you look a little bit yellow. And you have the result of the water extent in the right side in blue. So the other side are those elements, like we said, we mask only to have the water extent in our study area. Now the algorithm used for measuring suspended sediment, we will calculate the water quality by using a different algorithm, and we will compare them. The first one is the total suspended solid, TSM, of limb burner. And you can have reference to it through the article written by Limburner and al. In 2016. The concentration unit is in milligram per liter. We have now two definitions of this parameter, one for Landsat 7 and one for Landsat 8. So for this operation, we will use the red band and the green band for Landsat 7 and Landsat 8, but you will consider that the constants are not the same. So for this presentation, our focus, we use the Landsat 8. So we will use the formula of LYM8 as indicated here. For that now, we will calculate the value of the limb burner total suspended matter. You have the formula for Landsat 7, and you have the formula also for the Landsat 8 that is in the cell number 14 here. So for that one, we have defined it as limb LYM8 dataset return 3,957 times the dataset green plus the dataset red times 0.001 divided by 2 square, exponent 1.6436. We said we use the Landsat 8. So in for 15 cell 15, we calculate the value of the TSM, the limb burner, by defining it as LYM8 equal LYM8 ds dot where water extent. So you have to refer to your knowledge in the properties and the spectral reflectance, the spectral signature of water, and you will understand this selection of the red band and the green band. Later on, we will determine the quantile at 2% and 98%, and we will define them respectively as minimum and maximum. For the minimum, LYM8 equal LYM8 quantile 0.02, that coincides with the 2% dot value. and the LYM8 maximum, LYM8 dot quantile 0.98 dot value. The second algorithm is the suspended particle model, the SPM. That one also, the reference is the Zhongfeng Q and Al publication in 2013. The formula also is given here with X equal 2.26 red over green exponent 3 minus 5.42 times red over green squared plus 5.58 dot times red over green minus 0.72. And the SPM equal as 10 exponent x minus 1.43. So you see also the red and the green are still used for this formula. Then this function will enable us to calculate the value of the particle on suspension, the SPM of Q, written, and we have the formula here as defined previously. We will calculate the value of the SPM for Landsat 8 by using the extent of water as mass, SPM Q equal SPM Q ds dot where water extent, and we will determine at 19, cell 19, the quantile at 12% and 98%, like we did it for the previous algorithm. The third algorithm here is the Normalized Suspended Sediment Difference Index, the NDSSI, obtained from Hossein and al. 2010 publication. And the formula of the NDSSI use here the blue minus the near infrared divided by blue plus the near infrared. Here also you will see that the signature, spectral signature of the water will fit on this wavelengths where you have the blue and the near infrared. The NDSSI index value range will vary from -1 to +1, and value closer to +1 will indicate a higher concentration of sediment. Knowing that the near infrared, the water has a very low reflectance. Now we calculate the NDSSI by defining the NDSSI dataset, return dataset blue minus dataset near infrared divided by dataset blue dot plus dataset near infrared. We calculate the NDSSI for Landsat 8 using the NDSSI equal NDSSI ds dot where water extent, and we determine the quantile at 2% and 98% as done previously. And the last algorithm is the total suspended solid, TSS, obtained from Kwang and al. In their publication in 2017. And we have the formula of Kwang 8, define Kwang 8 dataset. We return 380.32 times dataset red times 0.001 minus 1.7826. Water extent. We define also determine the quantile at 2% and 98% to define the minimum and maximum respectively. Now we will compare the result of the algorithm that is given here, where you can go through, and we give a title. We ask the system to print the total matters in suspension by defining the legend. The black will indicate low total matter in suspension. The purple color will show, will indicate a medium low total matter in suspension. The orange will indicate medium to high total matter in suspension. And the yellow color will indicate a high total matter in suspension. And we define the title as the frame to represent the result. So the next slide gives us here the results of the 4 algorithms we have. We have on our upper left the TSM from limb burner. On the lower right, we have the TSM NDCI of Hussein. On the upper right, we have the TSM of Zhongfeng Qi. And on the lower right, we have the TSM Quang Pham. Based on our result, we notice that the upper left result, the upper right result, and the lower right result are almost close to have the same element of information on the level of total sediment, total material in suspension. What we notice is on the upper left, we notice that the northern part of the lake appears in yellow, orange. That indicates a level of pollution, as well on the upper right, as well in the lower right. The same element also between the limb burner result and the Quang Pham result, we observe on the western part of the image, we have also a concentration of total sediment that appear in yellow. And those elements indicate element in suspension into the water that is a beginning or an indicator of pollution in the quality of the water. So at least based on this element, the NDCI of Hussein give a reverse information compared to the 3 elements. But we consider here the 3, as I mentioned earlier, as indicating pollution in the lake, particularly in the northern part and the west side of the lake. In the northern part, it may be due to flow of element in suspension in the water that feeds the lake. And in the west side of the lake, based on discussion we had with some experts in Benin, it was indicated that in that west side, there are some settlements that may have deposited elements that contribute to the pollution of the water. This is what we have done using this water quality monitoring. It is an early warning element of information through the use of Earth observation to monitor the quality of water, and that will prompt decision on how to treat the water, but also the observation done through Earth observation should be completed by in situ sampling to confirm the quality and the level of pollution. That is one. And at the time of the sampling of the water in the lake, it should be done at a time that coincides during the passage of the satellite that we use. Here we use Landsat 8, so we have to look at what time, based on the revisit time of Landsat 8 above the lake, to do the sampling. So from that, we will be able to see if the sampling we made and the result we will obtain from the Earth observation corroborate or negate what we have as result. Thank you for your attention. And this is the reference we use, Badawi, Fiogbe, and Boko in 2010 to carry out the work we have done. Thank you for your attention.
Thank you so much, Soma, for this great presentation. We'll be looking at the session next week on combining the various satellite data. This one is in the coastal marine. Then also early in August, we'll be having the sessions on how to access the platform for other applications, and also cognizant of the opportunities to create a small session that we could describe how to access the platform using direct access. And the platform is grateful for the support from Helmsley Trust and Australian government and the Digital Africa implementing partners, especially AFRIGIST, Regional Center for Mapping, Agreement, and Sahel Observatory in Tunisia. This is quite good collaboration on where the program is going towards being in the continent. Sustainability is key, as well as the collaboration with all these partners who have really contributed a lot. So I wish to thank you everyone for connecting with us.